Yeah, we are pleased to welcome Hubert Chanson. He's professor at the School of Civil Engineering at the University of Queensland. He's a well-known international expert in hydraulic engineering and environmental fluid mechanics. He wrote quite a few books and numerous papers in all kinds of fields linked with hydraulic engineering. Today, Hubert will present about his personal experiences during the Queensland floods in Brisbane. And Hubert.
Thank you very much, Stefan. Yes, all right. Good afternoon, everyone. I will try to summarize both personal and professional experience during the flood, and I need to acknowledge first the number of people I work with, Dave and Richard, with whom we went in the floodwaters in the Brisbane River, but also my wife and my children who went to visit with me a number of dam spills. I want also to indicate that this is not a new presentation. I gave 2 talks at Engineers Australia in 2011 and 2012. I gave an invited lecture in France, an invited keynote in New Zealand on a number of conference papers, the last one in June this year in Brisbane. There have been an increasing recognition in our community that a number of urban developments located along watercourses are vulnerable to large floods. And this could be illustrated on this photograph, on this slide, by 3 cities in Northern Hemisphere, all flooded within about a 6 weeks time. And this in turn led to some very interesting hydraulic engineering with complex hydrodynamics associated with major sediment processes, as well as challenging fluid structural interaction, including the safety of individual floodwaters. But really one should ask, is it really new? Look at the statistics here. In fact, if you look at one of the world landmark, the Pont du Gard, which is a 3-tier stone masonry bridge built by the Romans about 2,000 years ago, carrying an aqueduct on the top, right here, that particular structure has experienced in excess of 120 major floods in the last 600 years, and it is estimated based upon our guess of the climatic condition prior to this record, that this particular structure probably experienced between 250 to 300 major floods, including probably 3 to 5 major floods during the construction period. Clearly, floods are nothing new, and maybe our Twitter-based, Facebook-based society become too complacent. My first experience of the 2010-2011 Queensland flood dates back from September 2010. In fact, I was in Europe at the time. I was doing some field measurements in the Bay of Mont Saint-Michel and in the Garonne River. I was doing field measurement in tidal bars, which is a different topic in itself. And when I come back late September, my wife told me, Hubert, it has been raining every day in September. I cannot get the clothes of the children dry. And again in October, and again in November. And by that time, I was able to see a few dam spills, Wivenhoe Dam, Gold Creek Dam, Little Nerong Dam. And then the big fall started to take place from late November to mid-January 2011, a very wet period which tragically led to the loss of 36 lives in Queensland alone, among which more than 20 people who were swept away by the floodwaters. My first experience with the big flood was probably my trip to the Burnett River catchment, late December, and probably the 2 most challenging memories of that trip were the number of road crossing closure. Numerous roads were closed, and we had to do probably twice the distance that we expected to do initially because of road closure. The second one was the operation of the Paradise Dam. And hopefully, if the video loads, and I apologize, it's an HD video which may take a few minutes to load, we will see 7,000 cubic meters per second discharging over the Paradise Dam. For those who are familiar with spillway design, we are looking here at an uncontrolled Auger crest, followed by a stepped chute, ending with a stilling basin operating as a hydraulic jam steering basin for small to medium discharge, and as a plunge pool dissipation system for large discharge. And one of the challenges, of course, is the magnitude of the rate of energy dissipation. The photograph that you saw corresponded to a situation where the spillway system was dissipating 2.8 gigawatt, while in 2013, January 2013, that particular system operated again, dissipating at the time 7.5 gigawatts. As we move in time, first week of January 2011 saw some massive rainfall over South Queensland, particularly the Condamine catchment. And while I visited Chinchilla, Dalby, and the surrounding area, one of the most interesting observations is the number of submerged road bridges. That particular bridge was probably 1 meter underwater, with about 8 meters of water beneath the surface. And at the top of the flood, there were an additional 8 to 9 meters of water. In fact, during the Queensland floods, a number of road bridges operated with large submergence ratio, and these were based upon guidelines derived from a PhD project supervised by Professor Colin Appelt, completed in 2000, which led to new design guidelines in Queensland, which I believe have been incorporated in the Australian standards. And then, second week of January 2011, the major rainfall over southeast Queensland. What you see here is the township of Marburg, about 60 kilometers inland from Brisbane, 60 kilometers west of Brisbane. And tragically, my daughter took this photograph about 2 hours after a 4-year-old toddler was swept away. Again, if everything goes well, we should be able to see a short video that I took while my daughter was taking the photograph. On the road in the foreground here is the road leading to the Marburg State School on the other side. And this was on Tuesday, 11th of January. As we move closer to Brisbane, this is the Mount Crosby Weir. Mount Crosby Weir is about 30 to 35 kilometers west of Brisbane. It's the last weir or structure across the Brisbane River, which is used to feed 2 water treatment plants. That particular photograph was taken on the Sunday, 9th of January. And this is the same weir view from the other side, this time 7 days later, while the peak of the flood was probably another 8 to 9 meters above what you see now. Of course, the road itself is beneath water. And then, there's a short video again. The road bridge is somewhere here. The previous photograph was taken on the other side. And then the floodwaters reach Brisbane. This is an aerial photograph of the western part of Brisbane. The Brisbane River flowing from the top to the bottom. The University of Queensland campus is located here. Rockley around here that we will see shortly. On Towong on Coronation Drive here, with a photograph showing Coronation Drive, Milton and Oakenflower in the foreground, on the Brisbane CBD in the background. Photograph taken on Thursday, 13th of January 2011. A short video taken in front of Towong of the CityCat terminal, video taken on the Thursday, 13th of January, about 5 a.m. The CityCat terminal is somewhere here. In the foreground, we have a bicycle path with 3 meters of water above. And you will see as the video changes that the water is basically spilling over the embankment, which is in fact Coronation Drive, the main arterial road leading to the city when you are coming from the university. Rockley What you see here is basically the main arterial linking Brisbane to Sydney by the inland route via Tamworth. This is the Ipswich motorway, underwater. The city on the on the Wednesday, 12th of January, and on the Thursday, 13th of January. And of course, the major cleanup afterward. And it's in that context that we decided to do some field measurement in Gardens Point Road, where we did a number of water elevation measurement as well as measurement of instantaneous water pressure and instantaneous velocity, as well as taking a number of sediment samples. This photograph taken during the flood, courtesy of ABC, show clearly the Garden Point Road, the blue dashed line. Our sampling side in red, it's not a conventional sampling side, it's where we could do something. The Brisbane River flowing from your left to your right around the meander with the airport on the river mouth in the background. And I highlighted also for your benefit the city gauge that we are going to see shortly in terms of the data. While on the other side in the foreground at the bottom of the slide we will have Kangaroo Point that we will see at the end of the presentation. We collected sediment samples in Garden Point Road, which is basically on the left floodplain of the Brisbane River on the Thursday, 13th and Friday, 14th of January. And we did a number of sediment characterization. Typically, we were dealing with cohesive sediment sludge with a grain size of about 25 micron. We are looking here at flocculated grain size. A relatively large fraction of organic content. And we did some rheological tests to look at the rheological characteristic of the sediment mud. What you see here is one test showing the shear stress, shear rate, horizontal axis, shear stress, vertical axis. All these tests were conducted under a very carefully controlled protocol to be able to be compared with other similar testing. In such a relationship, when we are dealing with water or with any Newtonian material, with log-log scale, we should have a straight line with a slope of 1 to 1. Any deviation from that straight line with a slope of 1 to 1 indicate non-Newtonian material. And what we have here is a typical S shape with difference between loading and unloading. This type of behavior is common to a type of material called non-Newtonian thixotropic material, ketchup, latonite suspension, concrete, behave like this. And by applying a very simplistic model, we're able to get some quantitative information on this characteristic. Importantly, with this type of material, it is known that at high suspended sediment concentration, we would have a non-Newtonian behavior. We also tested the acoustic backscatter characteristic of our system, an ADV system, as a function of the suspended sediment concentration, with typically the amplitude of the backscatter signal versus suspended sediment concentration. And we find what is fairly commonly observed with both ADVs and OBS system, an increasing amplitude with increasing concentration at low sediment concentration, and then a decreasing amplitude with increasing concentration. And of course, the key is to know which one could we use. And based upon some observation in the Brisbane River, we knew that we were in the upper part of this calibration. So let us now look at results on observation during the flood. We are looking here at observation that span from the Wednesday 12th of January to the Friday early morning 14th of January. The photograph on the bottom left shows Garden Point Road on Wednesday 12th of January. The flow from the bottom right to the top left. We see the ramp to the Captain Cook Bridge on the main channel of the Brisbane River being behind this ramp. The graph on the top shows a dimension sketch of the left bank of the Brisbane River. The main river channel will be right here on the right-hand side of the screen. The roots of the mangrove will correspond to the mean water level in absence of floods. We have the bicycle path here. We have the ramp to the Captain Cook Bridge, Garden Point Road, corresponding to what you see here on the photograph, the position of our sampling on car park underneath the buildings. And that configuration is typical of Garden Punch Road for about 500 to 600 meters. At ground level, the video to come will show you a view looking upstream of the floodwaters. The Brisbane River is on the far left, the ramp, Garden Punch Road, the ADV here on the car park of one of the buildings next to our deployment location. Some, pardon me, water elevation. On the black and white square, we looked at the water elevation at the city gauge. This is basically the water elevation measured 1.5 kilometers downstream of our sampling site. All the elevation being expressed in meter AHD. In blue, we see our own measurements of water elevation, manual measurements which were later on converted in meter AHD. And as we can see, at least for the two measurements immediately before and after the peak of the flood, our measurements were slightly higher than the city gauge data, and that is consistent with the measured friction slope of the Brisbane River during that period. For completeness, the dashed line at the bottom would have been the predicted water elevation of the Brisbane River at the city gauge in absence of flood. If we look now at a graph showing the period of sampling, we see again the city gauge data with the cross, our water elevation measurement, black square, and in red, we saw instantaneous water pressure measurement conducted with a pressure sensor sample at 50 Hz. The data showed fluctuation of plus or minus 10 centimeters, about a mean water level shown here in black. In fact, if we look more closely at the record, the graph on your right shows 600 seconds or 10 minutes of the record. Yes, it's 600 seconds. And we find that really not only we have rapid fluctuation of the water surface, but we tend to have some relatively slow oscillation of the water level about the mean. If we perform a spectral analysis, we find that there is a characteristic period for that signal of about 58 seconds. And more generally, if we perform a frequency analysis of the signal of both the water pressure and the three velocity components, we find slow fluctuation with characteristic period of about 50 to 100 seconds. We believe that these characteristic slow frequencies are linked with the natural sloshing frequency of the car park about 70 meters in length, and basically we had a kind of bathtub sloshing frequency in the car park, which were in fact linked with some excitation of the flow because of choking between the stairwell. This graph shows the time variation of the longitudinal velocity measurement in red as a function of time. Again, the city gauge data are shown here. We don't have a continuous record, but we get about 2 hours on the left, 2 hours on the right. The key things here is a large range of velocity fluctuation. Velocity fluctuating from 0 to 1 meter per second. And anyone with solid physical understanding knows that the turbulent flow does not fluctuate within that range. In fact, again, if we looked at 10 minutes of the flow, we saw the influence of this slow fluctuation about the mean. And in turn, we characterize the contribution of the slow fluctuation to the overall turbulence by performing what is called a triple decomposition, where we decompose the signal into a mean component corresponding to the black curve shown here, some high frequency component, which sometimes are called true turbulent fluctuation, plus a low pass filter component of slow fluctuation, which will basically characterize this slow fluctuation that we see here about the mean. When we conduct such a decomposition, we are able then to quantify the respective contribution of slow and fast fluctuation. This is illustrated on this graph by having on the horizontal axis the standard deviation of the longitudinal velocity component, the standard deviation of the measured longitudinal velocity component. On the vertical axis, this series of data with the asterisks correspond to the standard deviation of the slow fluctuation component, while the white square or losange here will correspond to the standard deviation of the true turbulent fluctuation. We find overall that the slow fluctuation contributed to 90 to 95% of the turbulent kinetic energy, while the characteristic of the high frequency through turbulence was close to characteristic observed in large rectangular channel on small estuaries. This graph shows the time variation of the instantaneous suspended sediment concentration derived from the acoustic backscatter data as a function of time. We find overall that the mean sediment concentration deduced from the acoustic backscatter intensity increased from about a mean level of 6 to 20 kilograms per cubic meter, but there is clearly some region where we have some very unusual pattern, both in terms of the acoustic backscatter signal as well as the velocity that we have not yet fully understood. Since we derive both the instantaneous velocity and the instantaneous suspended sediment concentration estimate, we calculated the longitudinal suspended sediment flux, basically the product of the sediment concentration times the longitudinal velocity. Both were measured in the same control volume with the same spatial and temporal resolution. We find overall that there is a reasonably large suspended sediment flux, but for the large data set here, where in fact we believe that the Garden Ponds Road section becomes disconnected from the main river. One of the questions that I had in my early presentations on this topic was how much sediment were carried by the Brisbane River. So what I've done is I've regrouped some of this information in the form of a time average suspended sediment concentration as a function of the time average longitudinal suspended sediment flux with the data before the peak of the flood and after the peak of the flood here in around the red cycle. For comparison, I've plotted on the same graph some field measurements of major river in floods, including the Amazon River, the Mississippi River, the Nile River, the Missouri River, the Big Muddy, and the Yellow River. The Yellow River data being typically around here with a few data in China of hyper-concentrated flow on the top right-hand side. For comparison, I have shown also the time average suspended sediment flux behind a tidal bore. For those who are familiar with a tidal bore, it's basically a big hydraulic jump in translation propagating upstream in a river, mixing everything and being able to carry a lot of sediment. And clearly, we can see this here. But let's make no mistake, the observation in the Brisbane River indicate that there were a lot of sediments in the Brisbane River in January 2011. And that led me now to the stability of individuals in floodwaters. Of course, if we look at from a theoretical perspective, we can derive the key forces acting on an individual standing in floodwater, the gravity force, the reaction force, the buoyancy force, and the hydrodynamic force, which is mostly the resultant of the pressure force on the submerged part of the body. Basic theoretical and dimensional consideration shows that the stability threshold of an individual in floodwater will be linked with the characteristic of the individual, height, mass, volume, so height and density, the fluid property, density and viscosity, the gravity acceleration, the bed surface slope on condition, on the flow properties, water depth, flow velocity, but also fluctuation in water depth and fluctuation in velocity. There are a number of design guidelines in North America, in Europe, in Japan, and in Australia, which rely upon a very limited series of experiments, physical experiments, mostly performed with individuals, men, women, and children, and a couple of studies conducted with scale models. These results indicated that there were two dominant modes of failures, by sliding in shallow water high velocity flow, and by tumbling, toppling, or tilting, whatever word you want to choose, in deeper water. Quantitatively, these results are often presented in the form of a critical velocity for stability threshold, vertical axis, as a function of the water depth horizontal axis, with data for adult on your left, children on the right. And Ron will see some of his data on the right-hand side. This experimental data showed consistently for all the data sets that the critical velocity for stability threshold decreased with increasing water depth. And for 2 of the studies, the results were independent of the type of failure. But let us look a little bit at the figure on the left-hand side. Look at the data scatter for some of this data. When one reanalyzes very carefully each of these data sets, we find that one study was performed with a professional stuntman. One study used emergency personnel, professional firefighters and swift water rescue personnel. 2 further studies used university students, including university athletes. Clearly, a lot of this data were highly idealized, not only by using fit people, but by having carefully controlled flow conditions, low turbulence, no sediment, no debris, good lighting, and everybody was secure with harness and ropes. Is it really representative? During the field measurement in the Brisbane River, 3 people, 2 academics and 1 technical staff, and that included Richard, Dave, and myself, went into the water. Our characteristic on the right-hand side, we are not fit, we are not expert in flood deployment, we are in our 50s, and we went 3 times in the floodwaters. And during 2 of these times, the flow conditions were unsafe for being able to stand without rope or on rail. This location of our 3 deployments are shown here with these rectangles, and during these 2 deployments, the flow conditions were totally unsafe. Why? Number 1, because of water surge. You may remember that we saw some slow fluctuation of water depth and on velocity. So every so often, the flow was reasonably quiet, and then suddenly a water surge comes, and we need to hang ourselves to the handrail. Another issue was the brown color of the water. When we were walking, we didn't know where we were putting our feet. Very dangerous in some situations. And we also were working at the first deployment in dark conditions using artificial lighting, and it was very easy to lose the balance. Our helpers, and we have 3 people, including the daughter of Richard, were helping us from above. They didn't go in the floodwaters. But they mentioned a further hazard: debris, trees, logs, trunks, rubbish bin, pontoon, passing in Garden Ponds Road, less than 10 meters from where we're standing, at typically speed of 1 to 3 meters per second. We didn't see them because most of them were fully submerged, but any impact of such a debris with one of us could have been tragic. So what I decided is to compare our observation with the previous guidelines, where we have the velocity, longitudinal velocity, vertical axis, water depth, horizontal axis. On the black square correspond to the time average velocity and the time average water depth at the time of deployment in the water, when we were physically in the water. The scatter bar in the vertical and horizontal axis correspond to the fluctuation in velocity and fluctuation of water depth for these periods. There's clearly no doubt that current guidelines were inappropriate in the specific context of Garden Ponds Road on the 12th and 13th of January. In fact, we propose something that may be more realistic, at least based upon the experience in Garden Ponds Road, to consider that the stability of an individual in floodwater, if someone has to go in floodwater, and that is arguable, should be restricted to this sole domain. And of course, engineers will always argue, why are you so restrictive? The answer is, would you let your wife, your son, your daughter go in Garden Ponds Road in this flow condition after what you saw? So the flood in Queensland between 2010 and 2011 led to major hydraulic engineering, and we were to some extent lucky to be able to do a unique field deployment in the CBD of Brisbane from the 12th to the 14th of January. As part of this effort, we did a number of measurements which were challenging itself, and I think one of the interesting outcomes is that by reviewing existing criterion for human body stability, we found that a number of guidelines are probably highly idealized and were not suitable in the context of Garden Point Road. But I think we need to look at the broader picture. This photograph is a photograph of the right bank of the Brisbane River at Garden Point Road. This is nearly opposite, sorry, at Kangaroo Point, my apology. This is nearly opposite to Garden Point Road. My youngest son was pointing to the peak water level in January 2011, and my eldest son was pointing to the peak water level in 1974. The January 2011 flood was only the 8th or 9th or 10th highest flood in Brisbane River. All the other flood levels here have been drawn at scale on the same photograph. I think clearly this type of photograph illustrates the need for our hydraulic engineering community to do more real research into the issue of flooding, field observation, and evacuation of individuals. We need to be challenged on clearly large floods, like the Brisbane River flood and the Queensland flood in 2010-2011, constitute a major challenge, unless we forget the 36 people who lost their life in 2010-2011. Thank you.
Yeah, thanks Hubert for this interesting talk. We've got plenty of time for questions, and we've got like a microphone here, and I would like to ask people to speak into the microphone, so we're recording this presentation that the people are aware what the question was.
Hubert, can you go back to your plot of the suspended sediment concentrations?
Oops, apologies.
Where you've got the Brisbane River ones against the other major rivers?
Yes. A couple of minutes, the system is a bit slow.
And my question is that you took your measurements pretty well up on the flood terrace.
Yes.
So your suspended sediment concentrations are not out in the main channel. My question was, are the concentrations from the other rivers also on the flood terrace, or are they in the main river channel?
You are correct, Ron. All the other measurements were typically in the main channel. Yes.
Your numbers seem to be on the lower side to the major rivers, which would explain it because you're up on the terrace.
And there's also, of course, a difference in instrumentation. A lot of measurement, for example, in the Mississippi and Missouri River were done with samplers, whereas then here we derive the sediment concentration based upon the acoustic backscatter, a technique which will be more consistent with the OBS technique. But again, if you looked at the data that I was showing before, and I hope this is going to take a while, all the data that were showing were mostly done by using samplers.
Yeah, it just wasn't. The reason I'm asking for the pictures, I can't remember whether it's a log scale or
it's a log scale, yes.
So there's quite a difference between your numbers and the others.
True.
But it can be explained.
Yes.
Okay, thank you. We'll come up in a minute.
Once I can get all the video.
Are we going to stop and wait?
I think you go ahead, Bill, because there's a few videos that need to go through this. So we'll try to get the slides shortly.
I guess I'm interested in reconciling the work that has been done with people in flumes and what you observed in Gardeners Road. And I guess my comment was, if we were to plot the turbulent fluctuations on the flume type data, I would expect the turbulence level to be about 10% of the mean value. That's actually been recorded there. What you've observed is that there are these surging flows happening in the urban environment, and I guess what I'm exploring is that if you took the upper envelope of where, I guess I'm interested in your comments from having been there. You said that the flow instability was one contributing factor. The upper envelope of the surging flow actually comes up and meets the flume data. So is it the case that you actually get to a higher velocity, and that's the thing that would actually reconcile your work to what's been done previously, because you've got these surges coming up. When it relaxes, you probably don't feel in danger. It's the actual peak surge that's going on in that situation. Do you want to comment? So I haven't expressed that very well.
I think the comparison with laboratory experiments is very difficult in the sense that in a laboratory you will do the test maybe for a couple of minutes. When you are 20 or 30 minutes in the water, as we were to install the equipment, we felt this regular surge of water coming at irregular intervals. Okay? I hope I'm going to get somewhere. So I think it's very difficult to compare the effect of slow fluctuation with the turbulence level that you could expect in a rectangular channel, because you cannot necessarily reproduce the same type of instabilities as you would have in a system like this. In fact, if we looked at the slow fluctuation, it took us nearly about 3 months to make a sense of what was the cause of this slow fluctuation. On the responses, the answer is it's local topography. So the local topography has a major impact on the flow instabilities which develop. If you looked at, for example, the car park of the building we saw in the video, whether you have columns or not, in itself will change the type of instabilities. Whether the stairwell are 5 meters apart or 10 meters apart will again change the type of instability that you could have. So I think it's become very difficult to generalize what is a local issue that you observe in an inundated urban environment versus what you could get in a laboratory.
You may come to the picture where you've got your plots on the data.
Sorry, which, the previous one? No?
Ones where you've got your circles, your variability between velocity and depth.
Yes. Yes.
I think what Bill's saying there is that if you go to the upper limits, that's when you may have been really feeling unsafe, and you actually didn't have the benefit of being able to be washed away. You were actually feeling unsafe and grabbing on, and that's your criteria.
Yes or no, because when you are working in the floodwaters, and even if your velocity is here, you don't know when the surge is coming. So if you know when the surge are coming, you would be able to work safely here, and then you grab yourself somewhere when the surge is coming. Yeah. But the surge, while there is a characteristic period that we could find, it was not as a periodic sinusoidal fluctuation.
But on that basis, even the one on the right-hand side would indicate that you felt unsafe at that average velocity and depth.
Definitely.
But the surge would have put you well into the danger zone of even our established criteria.
Correct.
So I think that's what Bill was trying to talk about.
It's a very interesting data set that you have, and one that I fear that the University of New South Wales would not let us collect, because I fear we would be in breach of many of our OH&S criteria. So you're privileged to have this data. I wonder though, I mean, when you look at the spread of data from other flume experiments and your data, you've already acknowledged many of the differences. I think when we've looked at the data, part of the reason that there is such a big spread is that the criteria for safety and the criteria for failure are quite different and in many cases subjective. So I just wonder, in the scheme of things, whether there's another 2 data points, because there are other data points from Spain where people have felt that they were unstable in very shallow, fast flows. So have you got you've also looked at the data. Would you agree, or do you have a further comment?
I think from my perspective, the challenge is what do you do with this data? Okay. I have a major issue when some consulting engineer in an office will try to use a guideline, whatever guideline it is, to pretend that people will be safe when they do a new development in a floodplain. And that's my main problem. I mean, my advice has always been, don't go in the floodwaters. That's the best advice we can give to everyone. However, the reality also is that there are people who have to go in the floodwater, the emergency personnel, and they need guidelines. And the idea for us in putting together this graph was really, look, if we were to provide some information on comment or suggestion to emergency personnel, what can we provide them on that what is got. But at the end, don't go in the floodwaters unless it's an emergency. On the emergency from here, you have to evacuate your house surrounded by floodwaters. And even in some cases, it's best to go to the roof rather than to evacuate. And the second situation is some emergency personnel need to be deployed. I think here it's a very, very difficult topic.
Conversation going. Hubert, I'm really interested in I think you said it was about a 60-second period that was causing this surge here. Sorry, I'm not questioning your ability. Please don't understand it. How convinced are you that it was this actual size that was going on within the car park itself? Are there other sources? Could there be big eddies in the main river that are sort of being swept up onto the floodplain that are causing these? You know, let me phrase the question a different way. What other possible causes of surge did you investigate, and did you eliminate them, or what's your level of certainty here?
Look, we started initially to look at the resonance of the Brisbane River Channel. That was our initial thought. And typically the characteristic period were smaller than the period that we observed. And that led us really to challenge ourselves what could be the cause. We don't pretend to have found the exact solution. I would probably say that I'm 90% confident that what we describe here is really what's happened. And one of the reasons for the high level of confidence is because there have been similar observations for a couple of studies conducted in laboratory of looking at intersection between building model and flood flow between building models, observing some form of resonance, which were directly linked to the topographic obstacle around buildings, for example.
I think even looking at Grantley's model outside here, under the sort of design flows he's been testing, you'd find these sort of oscillatory flows sitting in there, which the hazard would jump around between the buildings quite strongly. So thank you.
Thank you. Our friends from Manly Hydraulics Lab next door might be able to comment too, but I just wondered whether on this slower frequencies, whether on the any of the tide gauges, whether they sample in their raw sampling fast enough, if it's 1 second or something, to be able to pick any of that up.
No, the city gauge sample every 5 or every 10 minutes.
That's the raw sampling.
That's right.
Yeah, okay.
Maybe an actual would have had something like they had with the wave road, and the floods and all, they can sample much more quickly than when the water level of the wave roads would be accurate.
I mean, we are now upgrading a lot of our water level instruments to sample much higher frequencies, so we can actually resolve a lot of signals. So the old 15-minute average in the Stilling Basin are really days gone past. We do now deploy both pressure sensors and radar at most of our stations. I think all the ocean, is Rob here?
Yeah.
Yeah. All the ocean stations are now being upgraded.
They all have geosensors.
Yeah. So, you know, the data is getting richer.
Are those raw data retained?
Yes, we do keep samples of the raw data as well, yeah.
Are you familiar with the Graham's method for loss of life estimate for dam break studies?
Probably not. I'm familiar with a hydraulic study of dam break wave and the impact on people. There have been a European program as part of the CADAM study, and I'm familiar with this, but not by what you described.
Okay, just a popular method that we use to estimate loss of life, and there's got attributes in it that uses the depth and velocity aboard, and I was just wondering if you had any opinions on it. But all good, thanks.
So, not on the subject of the long period velocity and an influence it has on the error margin of your plot. I was wondering the non-Newtonian aspect of the fluid. Were you able to sort of estimate what would be its influence? For example, if you were discarding this 50-second oscillation and surge that is implied, but just look at the flume experiment, which would make, I guess, in clear water. What would be your opinion on where would it move, or how drastically would it move the curve in terms of safety?
Okay. I cannot answer directly your question, but I can certainly share a few thoughts. With thixotropic material, there have been some tests done with bentonite suspension using MRI, showing that a fluid would start to behave in a non-Newtonian manner with sediment concentration in excess of 10 kilograms per cubic meter. And clearly during the Brisbane flood we are above, most of the time 10 kilograms per cubic meter. The challenge that we have is, first of all, the research community doesn't know much about non-Newtonian fluid. And secondly, most of the work done so far has been done for pseudo-laminar non-Newtonian fluid. There is a total vacuum of information and research on turbulent non-Newtonian fluid flow. I would love that you speak to ERC and we put together an ERC discovery grant application to look specifically at this project, because there are definitely some major issues that should be looked at. One of the first things which come is, can we really use the Manning coefficient when we have a non-Newtonian open channel flow? And the answer is no. There's already been some work on this. And yet, we have an industry which continues to use an outdated coefficient.
Okay, excellent. We thank again Hubert for this interesting talk.
Thank you.